morning. I'm Jim, the interviewer, and today we have Eric Neives from Yaskawa Motoman Robotics, and he's going to talk with us today about human-scale automation. Welcome, Eric.
Thank you, Jim, and thanks for having me on Global Spec. Today's topic is going to be on human-scale automation. Human-scale automation in robotics. We really first need to talk about the history of the industrial robot. You know, industrial robots classically have been 6 degree of freedom or 6-axis machines, of certain size and scale. They grow and they shrink according to the application, but largely they are all variations on a theme. That has changed. The manipulator diversification in our industry is evident today. There are different configuration, different geometries of machines depending on the application that is we're going to automate. So you see that there are different robot manipulators for palletizing, different ones for deburring, arc welding specific machines, and then this new class of highly dexterous machines. But not all of these new robots are to human scale. This robot, for instance, is quite large. You can see the person standing at the bottom. This robot is actually specifically designed for the flat panel industry, and the glass on plasma screens seems only to get larger and larger. So we want to talk about how you get from the traditional 6-axis robot to this new class of 15 degree of freedom, highly dexterous, human-like machines. Well, first we need to understand the resistance to the 7 degree of freedom machine. These 6-axis robots are very successful. They've found application in many industries. They've been quite reliable. But they do come with a price, and that is interference. Anytime that there's interference, we deal with it on a 6-axis robot in a number of different ways. We change the layout. We change the end effector. We will put the robot on some sort of track to change the relationship between the robot and the work that's being done. We have done everything but question the fitness and suitability of the 6-axis machine. It's okay. Wasn't really a problem until density. All manufacturers now look at their floor space as a resource. And as a resource, it is to be optimized. The days of just adding real estate for the purposes of increasing production or throughput, those days are behind us. So what that means pragmatically on the factory floor is a great deal more density in a given space. You have a lot more equipment and a lot more processes happening. So for instance, it's a typical body line now where before you would have 2 robots on one side of the vehicle, you'll now have 5. Taken to its extreme, this is what density looks like. This is 10 robots on one side of a vehicle. 10 6-axis machines on one side of the vehicle, the driver's side, and imagine another 10 on the passenger side. The density is quite high, remarkably so. But you can see from the motions that it's exceedingly difficult to program this machine. There are interferences between neighboring robots. All of these positions and weld locations have to be sequenced in such a way to deal with interferences and such. The 6-axis robot had come to its limitation. Now we've always known that a 7-axis machine would help in that with 7 axes you can still maintain the pose, what we call the position and orientation, but you can choose the shape of the arm, what we call the configuration. with 7 axes, you gain the ability to program your way out of interferences. Let me be clear. On a 6-axis robot, you can choose any position in its work envelope and any orientation within that for that position. That's why they're successful. On the other hand, for any given, what we call a pose, this combination of position and orientation, a 6-axis robot will only give you one configuration, one shape. On the other hand, a 7-axis robot lets you choose not just the position and the orientation, but also the configuration. It's as if by adding one axis, you have gained another whole programming flexibility. So if we've known it, why hadn't we done it? What has kept the industry from moving forward with 7 degree of freedom construction? It was that we needed a new mechanism to drive the machine. This enabling technology is what we call the actuator, a high output actuator that would combine many elements into a single device. This high output actuator puts in one package all of the elements that were previously separate. The motor, meaning its motor stator, rotor and stator, the encoder, a brake assembly, a bearing, a speed reducer, all of these different components in a traditional construction have now been incorporated into a single actuator. What's the benefit? The benefit is that this actuator is hollow, and that's what was needed. You see, as you add that 7th axis, you now have to deal with cable management much more so than you did in 6 degree of freedom machines. Because they're so redundant, you could tie cables in a knot with a 7 degree of freedom machine. And that's why it was necessary to have an actuator where you could have a hollow bore and pass all the services through the mechanism. So these actuators have now been developed into a family of different outputs and ratings which allow for the construction of machines like this. Slim, 7 degree of freedom, redundant devices. What does that 7-axis flexibility afford us? Well, because the robot is considered basically a snake robot, it can move right along itself. It can be put in very tight spaces. In this image, what you're seeing is a robot actually feeding a machine tool, but from the inside. So rather than having to put the robot, as traditionally happens, in front of the machine tool, which is where the operator also needs to be, this robot can actually work its way through a small opening in the side of the machine and still tend it successfully. Well, a 7-axis manipulator is great, but how scalable is this technology? Well, we have found that with the range of actuators developed to date, there are 7 degree of freedom machines as low as 5 kilogram payloads and up to 50 kg machines. So how about dual-armed robots? Where does the human scale come in? You know, a dual-armed robot was the natural extension of the 7-axis machine. This 15 degree of freedom is just 2 of the 7-axis devices on a common rotating torso. So likewise, there is a family of dual-armed robots from 5 to 10 to 20 kilograms in payload. And they are on a human scale. For instance, the 10 kilogram machine is built to be 48 inches tall at the shoulders and to have the wingspan of a typical human operator. And what does that give us? It gives us the ability to do what were formerly tasks reserved for humans only. So in this example, this is an assembly process. And what I want you to notice is the dexterity that the robot exhibits and how it handles all of these different components without changing end effectors, without changing grippers. This is very significant. You know, in a traditional robot, if you have a single arm having to deal with multiple geometries of parts, then you would have to have a tool changer and switch from one end effector to the next to be able to pick up all the components. But we don't do that as people. When we deal with different geometries, we use two hands to do it. So what we've learned is that with bilateral control, with using two hands, you're able to reduce the complexity of the end effectors because you're using the dexterity of the robot as part of the grasping action. Dexterity versus complexity. You know, we've long known in the automation industry that a robot is a robust piece of equipment. It's an engineered device. But the end effectors, the grippers that are custom engineered for every single component, those are the ones that bring down the mean time between failure of a system. That's where sensors break down. That's where cylinders need to be replaced, etc. It's in the end effectors. So if you can reduce the complexity of the end effector, you have effectively improved the uptime of the machine. So as we explore more opportunities for dual arm and bilateral control, we find that we're looking for end effectors for these grippers that will also be flexible and also be able to deal with lots of different geometries. This is one such device. This is what's called an under-actuated grasper. In this case, there are 3 fingers. And those 3 fingers have 4 motors, one for each of the fingers, and a 4th that affects the relationship amongst the fingers. And with this under-actuated grasper, we're able to deal with a host of different geometries, holding a metal component in what would be a typical parallel grasp. These are flexible end effectors to go with flexible manipulators on a human scale. So what you're seeing now is 2 of these under-actuated graspers on a dual-armed robot, and notice all of the different components that we are kitting here. Now, in this demonstration, you see there are tires, there are different metal components, there are bolts to be picked up, etc. And we're able to use the 2 arms together and separately with these graspers and kit this entire assembly using one set of hardware. The other great benefit in dual arm or bilateral control is the ability to deal with non-rigid materials. You know, it's easy with one hand to pick up a piece of sheet metal. Once you've acquired it, you have it. It is essentially rigid. But that's not the case when you're dealing with non-rigid materials. You pick up a satchel with one hand and you have half a satchel laying on the ground. You need an ability to deal with 2 hands when you're working with non-rigid materials. In this case, what we're showing is a dual-armed robot working on medical tubing. Naturally, it's non-rigid. It comes coiled. We have to pull it off the spools, and we're putting clips on and cleaning them in solution and assembling this kit using this dual arm control. This would not be possible with a single arm, no matter how many degrees of freedom it had. It requires 2 cooperative robots working together. Same here. So this is a piece of foam or rubber being mounted on a mock mandrel. Very easy application for a person, exceedingly difficult for traditional automation. Now, however, using dual arm control, you can have one robot, one hand push while the other pulls, and vice versa, just like the person does. This is automation on a human scale. And this idea of cooperating between the 2 arms, is demonstrated here. In this case, the application is masking of PCB boards, printed circuit boards, before they go through a process. So the end effector on one of the arms is a masking tape dispenser. And you'll notice that the other arm will actually pull the tape out. They will together mask the board, and then it will clip it. We're now exchanging parts. We're doing material handling with the same machine, not a separate piece of automation for that. And now we'll pick a raw board, set it on the workstation, square it up so we know it's fixtured properly, and then now you can see the two arms cooperating to do the process. This is no different than the operator would be doing if they were in that robot's place. And you know, that is a measure of the success of automation. You know you got the automation right when you can pull a robot out and put a person in and nothing else changes. It may be counterintuitive, but it is true. If you can back the robot out and put a person in, then the automation is right. You know, we talked about how these robots have limitations. The largest dual-arm robot is 20 kilograms per arm, so about 40 kilograms. So like a person, it's not going to be able to pick up a component that's 200 pounds. But like a person, human-scale automation takes advantage of the same tools the operator would have. In this case, the robot is using a lift assist device, a jib crane, to do the heavy lifting, and the robot is just doing the manipulation. That's the way we do it as people. We let the machine do the lifting, and we do the localizing of the part where we need it. So notice how the robot comes in, engages the axle assembly. You can notice the jib crane up on the upper right, and now the robot and the servo track are manipulating the component. This robot would not be able to do that task without using human tools. But all of these applications we've talked about so far are what we consider blind applications. They are programmed. For many of the applications that we're going to be integrating robots for, we need more information. The environment is not 100% structured. We need vision. So what you're seeing here is a dual-arm robot performing an assembly task. But as part of this assembly task, it needs to recognize where that drive assembly is in space. So we're using a vision camera. You see the robot will pick it up, scan the part, and then set it down, and now the robot can pick up the part and deal with it adequately. We have integrated vision to dual-arm robots because as you put robots in more operations that were formerly done by people, you need to augment the robot's capabilities in terms of sensing. But something else is this idea of teleoperation. Teleoperation means there is no robot program. There is no robot program to even be modified by the vision system. Okay? In this case, teleoperation means taking control of that robot by means of some input device, whether it's a joystick or a haptic wand or whatever it might be, but being able to drive that robot as needed. This is important in applications where we need a man in the loop. Man in the loop requires a user application which is controlling the input device and the sensors and whatever else might be happening in the world, controlling the robot arm. You know, the traditional control structure for an application that uses information from the world is as seen here. You have connection between the robot controller and the PC, and in this case, between the PC and the robot. But for teleoperation, a traditional construction isn't good enough. You need a high bandwidth control, and that's what we're showing here is this 500 hertz link that allows the robot controller to talk to sensors at a very high rate of speed. So these teleoperation controls are important because they eliminate this barrier, this latency between what happens in the world and how the robot responds. This is significant when you need man in the loop for safety, man in the loop for control. They can drive the robot to exactly where they need it for maybe a handling operation or what have you, and know that the responsiveness of the manipulator is there. So all these capabilities are affording the entrance of robotics into non-industrial applications. They now become feasible. This is just a couple of images of some robots doing non-traditional work. Okay? We have Ned the bartender, and we have on the right an ice cream kiosk robot, if you could believe it. This robot is using its two arms. It's using all the same manual controls that the operator would have, and is dispensing soft serve ice cream, putting on the toppings, etc., and serving it to the people. So what other non-industrial applications become feasible? Well, once you have dual arm control and you have vision, right? Here is a blackjack dealer robot. It's using its two hands to deal. It's using a vision system to count the cards. It's using control algorithms to know whether there's 21 or it needs to double down. But all of this is possible because you have bilateral control. So, all in, dual arm robotics opens a host of applications for automation. It must be so. The world is built around human capabilities, and we are two-armed creatures. So we have built all of our processes around our capabilities. In the measure that robots become more human scale in size and human scale in capabilities, of course you open a host of new applications. 7-axis control was necessary to do it. The actuator was the seminal foundational piece to allow the construction. And I believe that that's what we have for you today. I thank you for your interest.
With Eric Neives with some questions regarding his presentation. Eric, what is next for human scale automation?
Next for human scale automation, I would say two things, collaborative work and mobility. Collaborative work, as robots become more human scale, more human-like, it becomes more important that they be able to work alongside their colleagues, people. The days of having robots in fences separate from the operators, those days have to be behind us if we really want to see automation achieve its full potential. So collaborative work is very important. Secondly is mobility. We know that people move to where the work is, and the same has to be true for robots on a human scale. Today, robots are largely tethered in place, and the work must come to them. So robotics is really looking towards mobility as a means of increasing flexibility in the plant.
what are the elements missing to get us there?
I would say perception and power. You know, perception is probably the most significant element in robotics in the future. And when I say perception, I don't mean sensing. Sensing is just data. Visual sensing is just pixels. What we need is perception, where you're able to analyze the data for a given purpose and do something useful with it. And I don't just mean vision. Vision is the most, I suppose, most important of the senses, but we need to incorporate force sensing, tactile feedback, and any of these senses is not as important by themselves as they are together. So perception, when we're able to look at these different streams of information and extract useful information for the robot, meaning position, what to do next, is the assembly correct, all of this is perception. Perception is necessary for robots. Perception is also necessary for collaboration. And I'd also say power is necessary. So as robots become mobile, we know they can't be tethered to power. Today's robots are three-phase machines, largely. So for them to become mobile, we need to be looking at different ways of having portable power to drive the mechanisms.
Will these new style robots replace six-axis robots?
Replacing the six-axis robots? No. Six-axis robots are very successful, useful tools. They're not going away. They've proven themselves in many, many industrial processes and applications. And really, you should never buy more axes than you need. And there are many tasks that can be accomplished with six-axis robots where there's no interferences or they're minimal, where you don't need the configuration programmability of a seven-axis machine. The seven-axis machine is necessary once you get away from tasks that are that structured. Once you've gotten to tasks where there's more assembly, where there's more interferences, where they have to work together, then the 7 and the 15-axis machines are really useful at that point.
Question number 4. As robots become more capable, will they take away jobs?
Okay. Will the robots take away jobs? You know, on a micro scale, you bring a robot into an operation for the purposes of automating a task. So yes, if you automate enough tasks, you have reduced the requirement for labor. So in that micro scale, yes, a robot is replacing human labor. But practically speaking, that's not what we see. What happens instead is this formerly, manual labor, this operator is now responsible for tending the robots themselves and programming and maintenance, and is able to focus on other higher value added tasks than maybe just loading and unloading some machines. So no, we don't see them cost jobs at the enterprise level. And certainly we don't see them cost jobs at an economy level. The watchword is productivity. And automation is just a tool to increase productivity. I don't believe productivity is a bad word. So the ability to do more with less, productivity, profit, is what drives our economy. We need to be conscious of the fact that, of course, while that may drive the economy, what drives our standard of living is gainful employment. So yes, there is this tension between employment and automation, but that is a bigger question than robots. We see that in medical coding software and your Xerox machine. There's lots of tools we use for productivity, and we accept them. Robots, I believe, sometimes get a bad rap because they are really doing active tasks and you can see them. But productivity is a good thing. So I hope that answers your question.
Very good, Eric. We want to thank you for coming in with your presentation today, and thank you for spending time with us answering the questions so well.
Thank you, Jim. And I appreciate your interest and hope that the information was useful to the Global Spec audience. Thanks again.